Hello, everyone. Thank you for joining me today. My name is François-René Lachapelle. I'm an astrophysicist, and I work as an application scientist at PHOTON ETC here in Montreal. I'm here today to talk to you about our deep cool infrared systems. So feel free to ask questions in the chat, or I might have a moment at the end to answer you, but my colleagues are also here to help you in the chat. So short-wave infrared solutions are more and more popular these days. As we saw throughout this conference, SWIR cameras are used for a broad range of applications. In research, it's used, for example, in the development of photovoltaic panel or in preclinical imaging of biomarkers in live animals thanks to the near-to biological window that allows to see through tissue. So also in industrial sorting, it's used in the recycling industry, where it's a great tool for plastic identification, and in quality check processes, like in agri-food industry or in the electronic manufacturing, or even in primary for industry, for drill core scanning, precision farming, oil and gas leak detection, to name a few. One of the key to this technology is the cooling system. So unlike in the visible, detectors in the infrared markets are relying on temperature stabilization and cooling to overcome their inherent noise from the dark current that would otherwise limit their signal-to-noise ratio and exposure time, and therefore a whole range of applications. So in order to properly cool our camera, at Photon ETC, we use 4 stages of Peltier thermoelectric cooling, and in a very specific and very low maintenance encapsulation design. So this allows to get down to a temperature of minus 80 degrees Celsius without the hassle of liquid cooling systems or consumable like liquid nitrogen. And the SWIR camera that you see here, it's a product line in the SWIR from about 500 nanometers to 1.7 microns in in-gas camera, and in the eSWIR MCT all the way to 2.5, or even extending further to 2.9 microns camera. So deep cooling of your cameras opens the way for low light application, as I said. The SWIR is a broadband imaging system that can be used as a standalone or integrated in a component on our systems or yours. So at Photon ETC, we also offer a broad range of product integration for our camera, like the SWIR broadband and hyperspectral microscopes. In the SWIR microscopy, we can go to about 100-time magnification. So on this slide, the image on the left presents an example of a very faint emission, easily detected thanks to our camera's high sensitivity. So the hotspots are infrared photonic emission from active transistors in the static RAM of a flash memory of a PIC microcontroller. Silicon being transparent in the infrared, this kind of image can be acquired non-intrusively through the backside of the silicon. So in-gas photonic emission is a useful tool in IC failure analysis. So very sensitive cameras are needed to get good images in low light SWIR microscopy. Narrowband filtering in wide field imaging also require high sensitivity. So for example, a filter SWIR can be used to study photovoltaic candidates. Electroluminescence, photoluminescence, and reflectance imaging can help identify the presence of defect and rapidly map inhomogeneities. The obtained result contribute to bringing to the market new, cheaper, and easy to process technologies such as perovskite-based solar cells to improve their manufacturing processes. In this example, the narrowband filtration is done with a tunable filter that we call the HYPERCube. This turns the camera into an hyperspectral imager. Such a photon-starved system would not be possible without a camera with a very low noise, like the SWIR. Photon ETC produce tunable filters with very narrow bandwidth and high rejection based on Bragg ratings. This can be used for global imaging, hyperspectral camera, where neither the sample nor the camera move, so we scan in the wavelength direction. The grandiose system that you can see on the right combines visible and SWIR global hyperspectral imaging with both macro and microscopic capabilities. This hyperspectral imaging device is a highly useful characterization tool for photovoltaic research and development. where the peak wavelength of the emission relates directly to physical properties of the material. We also couple our SWIR with high-throughput reflective spectrograph to do push-probe hyperspectral cameras we call LEOs. So this system uses a whole 2D matrix of pixel over camera to get both the spectral and spatial information at once, and then scan physically to get the full data cube. So this allows you to use on conveyor belts in the industry and in platforms, also as a benchtop installation. So the large aperture of this system combined with the reflective optics gives very high throughput, and a lot of light need fast and efficient scanning. At Photonics Industry, we work on a collaborative approach with our clients. So this high level of customization and integration capability of our products is a keystone in our business model. So for example, the development of the LEO's push boom scanner from our SWIR camera, then we adapted it and combined an array of these LEOs, scanning a wide range of spectral band into a versatile scanning system that can be used, for example, in plastic sorting, agri-food, or in the mining industry, to name a few. So for the latter, we mounted the scanning conveyor in a commercial container for on-site core scanning, and we provided adapted software solutions. So we have this multi-level engineering force for vertical integration to adapt our product to your needs. Another example of customization is the illumination system. It's a fundamental and often neglected aspect of SWIR and hyperspectral imaging. We're always working on developing innovative illumination solutions like LED panels, halogen reflectors, shaped lasers, or Bragg filtered tunable laser sources, and etc. So starting from the idea of improving capacities of SWIR cameras through deep cooling, we built around a whole range of optomechanical systems. Photonics Industry built a catalog of products through this idea of collaborative approach in high-tech physics and engineering to bring infrared hyperspectral in these innovative markets. So feel free to contact us through info@photonetc.com or go check out our brand new website at photonetc.com. For the remaining of this Photonic Plus conference, Marie-Christine Ferland, Business Developer Director, and Guillaume Gilina, Application Scientist, and I will be here to chat with you at our virtual booth. Thank you.